Right, then welcome again. This is the third and last talk I want to give you here this week. And this is about another paper. This paper has been finished. It's also on my webpage, so everybody who is interested in can read it there. Hopefully this time I will also stay in time. Yeah, yesterday I somehow managed in the second talk, right? But hopefully today it's even easier. Okay, so what I want to do is I want to integrate an integrated model of systemic risk in financial networks. And this is a model that generalizes the model I presented yesterday. Yesterday the model was just an example to illustrate how these systemic risk measures work, right? But today I really want to focus on these kind of equilibrium models and show you a generalization of a model that has caught a lot of attention in the past. So, okay, this can't work because the other thing is missing. Anyway, like this, that works. Okay, systemic risk. So, as you know, systemic risk is basically the risk that our financial system as a whole is susceptible to failures initiated by the characteristics of the system itself. And there are, of course, different transmission channels of systemic risk. So we have local and global interaction channels, of course. So, for example, you have direct contracts with other financial institutions in a financial network, right? You have creditors and borrowers that are basically bilateral agreements. And, of course, through channels like this, solvency, but also insolvency can spread through a system. Then, of course, you have also other channels which are more of global nature. You have information about the aggregate of the system. So, for example, you can count the number of defaults that occurred over a past period, right? And that might make you nervous, right? And that might make the market mood worse. And that can, of course, also change the way in which people behave. Another thing are price mechanisms. You can have, for example, have a downturn, and you can have liquid assets. And since in this downturn everybody has to liquidate liquid assets, the prices drop. And of course, the agents altogether influence the price that is decreased, and everybody is, of course, also influenced by this problem then, right? But it's not a local interaction channel, it's a global interaction channel, because it's not a bilateral channel, it's a channel which goes through an aggregate of the system, right? So that are local and global interaction channels, and we want to look today at direct liabilities, bankruptcy costs, cross-holdings, and fire sales. The whole thing goes back to this model I mentioned yesterday, the model of Eisenberg and Noé, right? That's this model from 2001 in management science. And this model has been extended a little bit by a couple of people. I list the literature here, but of course don't want to go through all the details. But what is missing so far in the literature is a really comprehensive model, right? Most of the models do, we take Eisenberg-Noé and then we introduce bankruptcy cost. We take Eisenberg-Noé and we introduce cross-holdings. We take Eisenberg-Noé and introduce price impact. That's it, right? That's what has been done in the literature. But of course, you can put all these things together in one model, right? That's what we do. And then analyze the model. Is there actually an equilibrium? How can you compute the equilibrium? That are mathematical questions you have to answer, right? And once you know how that works, you can, of course, also do case studies that now look at all the effects together and try to understand how they impact each other. So that's basically what we're going to do. If you have such a model, of course, the way in which you conduct numerical case studies is something which depends on your choice. So one way of studying the impact in such a model of systemic risk on the system is, for example, that you do it like we did yesterday. You say, we have shocks to the endowment of all the companies at the same time. That's what we had yesterday. Yeah, we have shocks to the endowment of all the companies at the same time. And in addition, that's what we did yesterday, we also assumed that all the shocks are random, right? So you don't know exactly what the shock is. You have a distribution of shocks, and they are all random, and they are all happening at the same time to all the companies in the system which you have. And of course, if you design such shocks, you have to specify how you do it. It's a multivariate random vector. That's what we had yesterday, right? And so you have to decide on the marginal distributions, you have to decide on the dependent structure, that's copula, right? So you have to fix the whole multivariate distribution for the shock. And then what we did yesterday is we then computed these systemic risk measures and looked at them. So systemic risk measures, what was that? We computed in a model all the capital allocations that have the property that if these capital allocations are fixed at the beginning, the shock occurs, the systemic interaction also takes place, that at the end we get at a random outcome for the economy that's acceptable. That was the idea yesterday, right? Today we will conduct the numerical case studies in a different way. This is also not new, but it's a different alternative way, and we will use this here for the analysis. So what we do today is we have a system in which we also have randomness. I introduce the randomness later. And then we just take one bank and kill it, right? And then we just look at how this shock to one bank propagates through the system, right? It's a different kind of analysis. Yesterday we had the analysis, what capital do I need actually to make the system stable, right? And today the analysis is the analysis, if we kill one bank, how does it propagate through the system, right? Of course, in this model, you can also do the analysis we did yesterday, no problem, you can do that. That doesn't depend on the model, right? Whether you do this analysis or this analysis. It's just a choice you make at the end when you do your numerical case studies, what kind of stuff you want to look at, right? And so today we do the second thing. So, yeah.
Your first bullet point emphasizes the endogeneity of these instabilities.
Yes.
Will you endogenize shocks in this comprehensive model, or will they remain these external lightning bolts?
No. The systemic risk is endogenous. Why? Because we model all the interaction channels, right? Yeah, so the way how a problem in the system propagates through the system is endogenous. However, the initial problem is triggered exogenously. So it's exactly in this paper here in the case studies like I mentioned. We kill a bank, one bank, and then killing one bank is not systemic risk, right? Killing one bank is idiosyncratic risk. One bank is that, right? And what we analyze is what is the effect of killing one bank on all the other banks and the whole system. And the propagation channel, that's modeled endogenously, right? So that's how this model is set up. Yesterday we had the same situation. We have a model in which you have propagation channels and interaction channels that are in the model. The shocks you do are systematic shocks. Systematic means you have underlying risks that affect all the banks at the same time. But systematic has to be distinguished from systemic, right? Yesterday we had systematic shocks, so we randomly influence the endowment of all the banks, right? But this has nothing to do with systemic, because it's an exogenous random shock to all the banks at the same time, right? And then we had this propagation mechanisms in the system, and that led at the end to some random outcome for the society, right? And then yesterday we were investigating how much capital do you need in the beginning to kind of stabilize the system, right? So today we take a different view by looking at the number of contagious defaults, but in the end the model methodology is similar to the example we used yesterday, right? Okay, so what do? We have a comprehensive model of financial networks with direct liabilities, bankruptcy costs, cross-holdings, and fire sales. So this is a recent paper, which is also on my homepage if you're interested. We prove the existence of the equilibrium. We derive an algorithms to compute the equilibrium and prove that the algorithm actually converges correctly. in n+1 steps if we have n banks, and then we do numerical case studies. And here I focus on the second part. The first part was done yesterday. So what's the integrated model? So what we have here is we have banks which are connected to each other through 3 channels. So we have direct liabilities. What does it mean? So we have a network of banks, and the banks have nominal liabilities against each other. So these nominal liabilities are, as you know, they are just promises, right? They're promises, but they have to be honored if the bank can do it. Then the second channel we have is cross-holding. So now we also assume that the banks in the system own each other, right? So a bank, right, itself might have shares of another bank, right? That's allowed, right? You can be a shareholder of another bank. That's what's called cross-holdings. And then we have fire sales. So fire sales means all the banks are exposed to the risk that the price decreases in some common asset holdings. So they have some external assets, which are not assets inside the banking system, that are assets of other companies, right? Stocks of some other companies in the economy, right? Or other products, right? You can have bonds or whatever. And these products have the problem that if they are all sold at the same time, the price decreases, and this is of course a risk to each of these things. In addition, we also have bankruptcy costs, which we will implement, and then we will see how the system works. Mm-hmm.
How realistic are these cross-holdings for banks?
Yes.
To what extent are banks really holding equity in them?
Yeah. It's in fact the case that banks do actually have cross-holdings, and I don't recall the exact number. We have that in the paper in a footnote, but what we assume, I think, is that 15% of the bank's net worth is held by other banks in the system. 15%, that's the parameter we use in our numerical case studies. And according to some papers, that's about a realistic estimate of this number in certain banking systems, right? I have to make that a little bit conditional on saying on certain banking systems, since I do not precisely remember, right, what these papers did. But we have a footnote in the paper that's actually mentioning this point, how we choose a parameter.
Banking
right?
systems, it's much less than 15%.
It could be that in some banking system it's a different number. But the reference is in the paper, in a footnote. And that's also the number we choose for the simulation, right? So the number is not just picked ad hoc at that point, right? This cross-holding number, that's based on some other papers, right? Of course, I cannot say that I can 100% guarantee that the estimate of this number in the other papers is somehow completely correct because, yeah, I mean, we just took it from there, right? Yeah. But it's a phenomenon that exists, right? And you will see how we model it, right? And of course, you can question the way how we model that as a transmission channel of solvency, right? But we'll see that in a second. So we have n banks. This is what the banks are. And then we have interbank payments. So interbank payments are payments made from one bank to another bank, right? And of course, these payments are based on promises, but they are also based on the solvency of the bank, right? If the bank is not solvent enough to fulfill the promises, it pays less. So this vector P is the vector that assigns to each of these banks what it actually pays out, right? Yeah, in total to the other banks in the system. That's what this vector signifies. So the first component of this vector is what bank I pays out to the other banks according to the liabilities it has. P2, what bank 2 pays out to the other banks according to the liabilities it has, and so on. So that's the P vector, right? We'll see how we derive the vector, right? It's just the description of the vector. So each component of this P vector is the sum of all the payments to the individual other banks, right?
And you have a time dimension, or you?
It's a one-period model, one period, right? So we have a vector of net worth. I'm also explaining later how we compute it. So the net worth is basically just the value of the assets of all the banks at the end of the period, right? What do we have as a bank? Assets, cross holdings, What payments do we receive? That's what W models. So it's also a vector because we have the n banks. Each component refers to one of the banks. So the banks have external assets and yeah.
Sorry, what we have after paying, or the vector of net worth is what we have after paying all the other banks.
After clearing, right? Exactly. So this is at the end, and this is also at the end, right? So we have a system we compute in equilibrium, and P and W are computed in equilibrium. So they are solutions to the problem, right? They are not given; they are solutions to the problem. And these quantities here are partially given and partially solutions. So R is the cash assets of the bank. So we have n banks. So for each bank, we have to say how many cash assets each bank has, right? That are the liquid assets, right? And the second is we assume that the banks have also illiquid assets. So that's modeled by S, is another vector, right? So each component tells me how many illiquid assets do I have as a bank. And the liquid assets, of course, have a price. The price itself, Q, will be computed in equilibrium, right? So that's not a given quantity, that's a computed quantity. So this is computed in equilibrium, this is computed in equilibrium, this is computed in equilibrium, but these things, they are given in the beginning. Later on, they will be given randomly, but they will be given, right? So that's a financial system, right? Banks, the realized payments, the net worth, the cash assets, illiquid assets, and the corresponding total value of external assets is, of course, for each bank computed as a cash assets plus the number of illiquid assets plus the price times the price of the illiquid asset that's computed in equilibrium, right? Okay, so now I specify what are the liabilities inside the banking system. So we have a nominal liability matrix, and Lij displays the interbank obligation of bank I to bank J. So this is what I promise. I tell you, you get 500 million tomorrow or something like this, right? So that's what this is. But we also have liabilities to entities outside the system, and they are modeled by this other vector that you hopefully see in a second.
It's because of the insect.
Okay, yeah. So the computer projector gets scared, right? Yeah.
No, because it confuses the B with the blackboard.
Yeah. Okay, good. So it's B, right? Yeah. Okay, so L, that are the liabilities to entities outside the system. And so if you compute the vector of total liabilities of bank I, you have to sum up the liabilities of bank I to all the other banks in the system, plus the liabilities of bank I to entities outside the system, right? That's what this is. This is a total liability vector. And PI, right? This is a total liability vector, and PI is the I's component. That are the total liabilities of bank I to somebody else, right? Okay, and then we have realized payments, which are computed in equilibrium, right? And the realized payments is that what bank I pays in total to the other guys, and that's of course less or equal than what bank I promises. And how much that will be has to be computed in equilibrium. Okay, so then we compute a relative liabilities matrix, and that are the liabilities to each of these entities divided by the total liabilities of bank I. Why do we do that, right? Because when we have clearing, we want to have that clearing is proportional, right? If bank I doesn't have enough money to fulfill everything, right? It has less money, and then it pays out to all the other entities according to these proportions, right? That's the idea, right? So if some other bank has 50%, and another bank has also 25%, and another bank 25%, and bank I doesn't have enough to fulfill the obligations, then from what bank I has, the banks get 50, 25, 25% respectively, right? This is the idea. Okay, so that's this matrix, the relative liability matrix. So that's a network, kind of. And so each bank has income from liabilities, and the income from liabilities is, of course, just the sum of the payments they receive from the other banks, right? And the other banks just pay out what they have, right? So that's a PJ, and the P vector needs to be computed in equilibrium, as mentioned before. I'll tell you what the equilibrium is later on. Then we also have cross-holdings. What's cross-holdings? Cross-holdings means that you owe a share of the other bank. And as I mentioned before, there were some papers, right, you pointed out that this is in some banking systems about, let's say, 15%, right? I don't recall exactly the details of this analysis, but that's also the number we use in the numerical case study. So we have a cross-holding matrix, and Cij denotes a fraction of bank I that is held by bank J, right? So Cij, right, for each bank is what fraction of I is held by J. And if you want to compute...
Is that really significant?
Well, there are some papers out there in the literature, I don't recall the authors of the paper, but we mentioned that in our paper, in a footnote. And so there are some papers who estimate that cross-holdings are about 15%.
Cross-holding in which sector?
In which sense?
In which sector?
In the banking sector. Yes. Yeah. I have to look at these other papers again to give you a really precise number, right? I just know we looked it up, found some papers and quoted them in a footnote to justify why we picked 15% in our numerical case study, right? But I cannot give a completely precise answer in the sense that I don't recall all the details of these papers, right?
So what is WJ?
Yeah, WJ is a net worth of bank J. I'll explain on the next slide what that exactly is, but it is interpreted as the value of the other bank. So yeah, it's roughly. Yeah, I'll explain it how we do it.
But again,
right?
it's the same question as yesterday. But
Mhm.
why are you calling this income?
Hmm?
Why are you calling this income? Because it's I own something. It's worth WJ. I own a fraction CJI of that thing. Well, it's a wealth.
Okay.
It's not
So-
income.
Yeah,
Cash
you're
flow.
right. I mean, maybe our wording is not perfect. I agree with you, right? But let's look at the next slides and we see what we want to say. If we look at the formula, hopefully it's clear what the model is. And I agree with you that maybe some of the words I picked to denote some of the objects in the analysis are a little misleading. So we should probably change that. No question about it. But that doesn't really change the model. So the idea is we have something which we call essential networks. Of course, also this word is debatable. This is really a good idea to call it like that. But if you look at the banks, right, then the networks worth of the banks is computed by the cash the banks have in this model. The cash the banks have in this model. So we have just two external assets, cash and illiquid asset. Then the illiquid assets you have times the in equilibrium computed price of the liquid asset. So that's what the external assets are worth. And we have here a vector notation, right? Because we have n banks, so you can read this component-wise. Then the next thing is the banks receive payments from the other banks once the market has cleared. So the other banks, they need to fulfill their obligations if possible. If not possible, they have to pay out everything what they have because they are in default, and then they pay according to the proportion of the original liabilities out, right? And this can be computed in this model as the transpose of pi times p, right? This is just writing it down in matrix notation, what I said before. So then we have another term, and Rama pointed out that this should rather be called the value and not the income. That's completely right. And that's the value of cross-holdings. So the other banks also have some net worth. And if the net worth is positive, you have a value. If net worth is negative, then the equity value is 0. Net worth also measures the liabilities that are still outstanding. How we define it is the reason why I have here to take a maximum with 0. And then C transpose times this W maximum 0. This is the value of the cross holdings. And from this, we subtract the promised obligations, right? So in other words, if this object here is positive, then the corresponding bank is able to fulfill its obligation, and there's also some value left, right? If this is negative, right, then this signifies the damage this bank causes to the system, right? And using Banach's fixed point theorem, right, you can show that the net worth conditional on a given P and a given Q always exists as a fixed point to this equation, right? This can be shown. The P and Q will be endogenous in equilibrium. We'll come to that, right? But we need this as a preparatory step. So, given a P, given a Q, you can compute a net worth vector as a fixed point to this equation. And in order to prove that, you use simply Banach's fixed point theorem. That's all. Contraction mapping theorem, right? That's all you need. Okay, and the vector is always unique. And it is also increasing in P and Q, right? Which is understandable. If more is paid inside the system, right, then of course net worth increases. If the price of your external assets increases, then of course you also have more, right? So that's what this
P
is.
is the price of the liquid asset?
No, Q is the price of the illiquid asset, and P is the equilibrium clearing vector. So it tells you what the bank in equilibrium pay to each other, right? So P I is the total amount of liabilities that bank I fulfills. So it's a sum of all the payments that are made to the other banks in the system and to the external agent, right? That's what it is. Yeah.
First, what is your bankruptcy rule? And second, you mentioned at some point about the bankruptcy cost. Where does this show up?
Not yet.
Not.
But what's the bankruptcy rule? The bankruptcy rule is this W is non-positive. That's insolvency, right? If the W is larger or equal than 0, it means that what you have, this is here, is larger than what you owe, right? So you are solvent. And if this is negative, then what you have is smaller than what you owe, and then you are insolvent. That's the bankruptcy rule. Okay, so now we want to step for step model the other objects in this system endogenously. So the first thing is we want to talk about deriving the price of the illiquid asset. So we still fix the P exogenously. We still assume that the payments of the other guys are given. So that's like in game theory, right? We assume that all what the actions of the others are given, right? And then we compute what's somehow the payoff to me, right? And later on we will compute an equilibrium. The equilibrium means that my payments, right, are feasible given the payments of all the other guys and vice versa, right? That's the equilibrium, that we have the fixed point. We are not yet there, but here we just compute the Q. So we assume that the P is given, and here, that's also a question Rama asked yesterday, we assume that the inverse demand function is actually given. So it's not derived in equilibrium. Here we have an equilibrium. The equilibrium is already complicated enough. And so some objects are specified exogenously. So the inverse demand function of the illiquid asset is a given. It's exogenous, not endogenous. But you'll see that the equilibrium is complicated enough. So at some point one needs to stop making the model more complicated. But of course one could make it more complicated in the next step if desired. So the inverse demand function is here simply assumed to be exponential. And theta is the quantity of the illiquid asset that's sold in the market. So now, of course, the theta itself depends on the P and the Q. And the Q itself is a fixed point to such an equation. And now we have to set up the equation. So this is explained here. So the theta is a quantity of the illiquid asset that is actually sold in the market. How do we get this quantity? Well, we have to sum up the quantities sold by all the banks in the system. So we have n banks, so we have to make a sum over all banks in the system. Then, of course, we sell only what we have to sell, right? Yeah, because by selling we diminish the price, and if we have it, then it's valued by the price that's out there. So selling doesn't make sense if it's not necessary. So we sell only the minimum of we have to sell, or what we can't sell, that's what we have. So if we have to sell a lot, we can of course only sell what we have. But if we have to sell less than we have, then of course we sell only what we must sell, right? That are the two terms. So what do we have to sell? Well, I have to pay PI bar. That's my liability. Well, how can I pay it? I can use the cash I have. I can use the payments I receive from the other banks. I can use also the value. That's the assumption of the model, right? I can also use the value I have in cross holdings. And if that's not sufficient, then what remains is my holdings in the liquid asset, right? Because that's all what I have. I have the liquid asset, I have what I receive from the other banks, I have my cross holdings, and I have my liquid asset. When I subtract from what I have to pay everything what I have, except for what I have in the liquid asset, right? Then the difference exactly gives me what I need to pay using the liquid assets. And the liquid asset is, of course, the asset I want to use last because I diminish the price, right? All the other things don't have any price impact. So I compute this term, and of course, it's what I still have to pay. Only if that's positive, then there's something remaining I have to pay. And in order to obtain the number of illiquid assets I have to sell, the number of shares, I have to divide this, of course, by the price, right? That gives me the number of shares. So that's what this is. And if I sum all these things up, I receive the total quantity of illiquid assets sold in the market, and then I can plug this into this equation, and solving for the fixed point Q, I get the equilibrium price of the liquid asset in the market, right? That's how it works. But the model is not finished. You see, it's getting a little bit complicated, the model, but it's all done step by step, and we are putting it together. Now the bankruptcy costs come, right? You asked the question, right? Bankruptcy cost. So the idea is, if a bank is in default and bankrupt, there are legal and administrative expenses that may be incurred that reduce the amount of net worth that can be used to fulfill liabilities. And what we assume is that the net worth of the bank basically stays as it is before. But if you have a bank which is in default, then only a fraction of the assets is allowed to be used to serve for fulfilling the obligation. And a fraction of that goes away to some lawyers or other people, right? Who also want to make a profit from that. So those guys who love a financial system in distress, right? Because they make the money from that. So, and so we have an external recovery rate and an internal recovery rate. So and this is now the definition of the price payment equilibrium, putting everything together. So how does it work? Well, here we have the function psi. The function psi depends on the p vector and the q number in equilibrium. The p vector is the vector of total liability payments made by the banks, right? If n banks, this vector has components p1 to pn. P1 is the total payment bank 1 makes to all the other guys according to this proportionality rule. And this is here what's in the first n components. And the last component is the price component, so that's the q, right? So the q thing, that's something I already explained earlier, right? So I don't really have to go into the q. If the p is computed, then the q, how that's computed, I already explained it, right? But now I have to compute the p simultaneously in equilibrium, in the fixed point, right? And so how do I do that? Well, if a bank is solvent, So if the cash plus illiquid assets plus what the bank has inside the banking system, so the payments from the other guys plus the cross holdings, the value of the cross holdings, if that's bigger than what the bank has to pay, then the bank pays what it has to pay, of course, right? Because then it's liquid, right? It's solvent, then it pays out. If that's not the case, so if it's insolvent, then the bank pays out a fraction alpha of the external assets, so a cash assets plus SI, the illiquid assets times the price of the illiquid assets, plus beta, that's a fraction of the bank, the assets inside the banking system. So that's beta times this term here. So that's what the other guys pay to you plus the value of the cross holdings, right? And here is how the theta is computed again, depending on the P and Q. And so this is now the model. This is now the model and the definition of the price payment equilibrium.
So I don't answer what alpha and beta mean here.
Okay, alpha and beta, that's this here, the external recovery rate and the internal recovery rate.
I thought that in Heisenberg, no, the recovery rate is endogenous.
No, it's different. The recovery, yeah, okay, so I agree with you that
So
the language might be a little bit confusing. Eisenberg-Noé have a model which, as we do, computes the recovery in equilibrium, so it computes it endogenously. What is not present in Eisenberg and Noé? Bankruptcy cost. So, the recovery or the payment vector, that is the vector P star, which is computed in equilibrium. In contrast to our model, Eisenberg and Noé do not include a lot of the effects which we have. In particular, they do not include any bankruptcy costs. So in the Eisenberg-Noé model, this alpha is always 1, and this beta is 1, and this term does not exist, and this term does not exist. This is Eisenberg-Noé, and also this does not exist in Eisenberg-Noé. So the Eisenberg-Noé model computes the payments in equilibrium, so that actually means you're completely right. It computes the recovery in equilibrium, but it does not have any bankruptcy costs. So in that sense, maybe the wording we use here is not good, because this here refers to the bankruptcy costs. So alpha is actually what the obligor receives as a fraction of what is left.
Yeah, so it's the reduction in recovery rates due to bankruptcy.
Yes, exactly. So the wording which we use here is apparently not very good. I agree with that. Yeah, we have to improve on the language, right? Yeah, but that's a difference. Yeah, I keep that in mind. That's an important point, because otherwise it's a little confusing, right? So that's the difference. So Eisenberg-Noé, they don't have illiquidity, they don't have bankruptcy costs, they don't have cross holdings, and of course they also don't have this term here due to the liquidity. So that's a system which includes now bankruptcy costs, illiquid assets, cross holdings, and in addition, of course, classical Eisenberg.
So what is the last one?
The last term is the term that computes the quantity of the illiquid asset that is sold in total by the guys in the market, according to the explanation I gave here. So you have to pay P bar I. You can pay it using your liquid assets. You can pay it by the payments you receive from the other banks. And we also assume that also the value of the cross holdings can be used in order to pay your obligations.
Because you have a one period model.
Mm-hmm.
So at the end of the period, everything is liquidated. That's the meaning of the Eisenberg-Noé.
Yes, here it's the same,
Everything
right?
is liquidated,
Yeah.
all obligations are fulfilled or you default. So
Yeah,
I
there's a
don't
little
understand
difference.
what this thing about selling the asset is.
Yeah, yeah.
Everything is liquidated. Whether you want it or not, everything will be.
Yeah, I understand your point, but there's a slight difference. The assumption of the model is the following. The illiquid asset at the end of the period is valued by its price. And the price is computed according to the inverse demand function. However,
But what
the,
because
I mentioned
everything
this
is
before.
liquidated.
No.
My point is this.
Yeah, I
If
see
you
your
have
point,
a
but I'll try to
one-period
explain
model,
it.
If you
Yes.
have a one-period model,
Mm.
how can you distinguish between liquidity and solvency if you have a one-period model at the end of which everything is liquidated?
Yeah, no, I mean, it's a slightly different. I mean, your presumption that everything is liquidated, that's not done in the model. So I'll explain it. The idea is the following. You have liabilities, and for the liabilities, you use your cash assets, the money you receive from the other guys, and the value of your cross holdings to pay that off.
That means everything is liquidated.
No, just wait. I'm not finished, right? Otherwise, it's not possible to understand it if I cannot explain it, right? So I have to finish my sentence. So this is the residual value of the liabilities that I cannot fulfill if I use this, and this, right? And now the model is a little bit different than you say. It's like this. I still have a package of my illiquid assets sitting on my account, on my portfolio, right? This is now how it works. And the assumption is now that only that fraction of the illiquid asset that needs to be sold on the market in order to fulfill the obligations I have, that only this proportion of the illiquid assets is taken into account to compute the price of the illiquid asset. And then, given the computed price, right, I value the assets, the illiquid assets, mark to market. That's the difference, right? So what I do is I compute how much illiquid assets actually have to be liquidated in order to fulfill the obligations. And this fraction is a fraction that's used in order to compute the price of the illiquid asset. And then I use this price and mark the assets to market, right? This is the difference. So in that sense, I hope that answers your question. The valuation and the liquidation, right? These are here in this model two separate things, right? Liquidation.
I have an idea. I have an idea.
Yeah, in this model, right?
I have an idea of how
yeah.
to
Explain to us.
justify,
Yeah.
tell a story that justifies what you're doing. If I understand what you're doing.
Yeah.
What you maybe should be saying is that this is a snapshot of a multi-period problem. You're assuming the form of the value function going forward.
Yeah.
And that's going to be different if you have to liquidate the assets now versus if you can keep holding them. So you have a valuation which you think is a reasonable valuation that might come out of a dynamic program if you had a dynamic model.
Yeah. Okay. So
That may be.
If you have a multi-period problem, I buy that because then you can distinguish liquidity from insolvency, the liquidity from insolvency. But since you have a one-period model and you're doing what you're doing here, you see, if I to compute all these things, you need to have a full-blown liquidation of everybody and then obligations are fulfilled. Otherwise, there's no reason that the price will take the value you're saying, because unless you have liquidation, you can have a zombie bank which is insolvent, and why is it not going to?
well, the point is, I see your point, but the point is, these are the equations how we set up the model. And these equations say the story that can be told is a story I mentioned. Of course, you can say you don't like the story. You want that everything in this model is liquidated at the end. But the story I tell is that liquidation is only what is done to what needs to be liquidated in order to make the payments at the end. And valuation here in this model is a different thing. So valuation takes place of the residual, which then remains out there. That's then valued by the price that's triggered in this illiquid market, and then we mark everything to market. That's just how these equations work. I agree with you. This is debatable whether you want to have a model like this, right? But this is a model. This is a model, right?
Look, you say at t equals 1, bank I needs to pay out its liability.
Yes.
LIJ.
Exactly.
Why does it need to pay out its liabilities? It's because you think of them as cash flows. You don't think of them as mark-to-market value of something which can be paid in 30 years. You think of them as cash flows. They're actually cash flows. So you're saying all these things are cash flows. Whereas in a banking portfolio of like 30-year bonds, you don't need to pay them.
No, you're
Even
right.
though you might be insolvent from the point of view comparing the accounting values, that doesn't mean you have to pay anything. I might be insolvent, but that doesn't mean I owe anybody any cash flow right now. So there are two things. Insolvency is just accounting, and then there are the cash flows. Maybe I don't have to pay anybody anything right now, but I'm insolvent. So these things get intermingled here.
So, yeah, part of this is a complaint about the bankruptcy rule.
But I understand
So
your point.
If you're gonna, it'd be nice to have a consistent story. If this is a snapshot of a going concern and what we have, and here is evaluation of what it's worth going forward, why are we liquidating everything? As much as we are. I had just a mechanical question. Those cross holdings, they all get liquidated? Are they positive and negative?
Only if they are positive, and if they are negative, they don't count, right? So it's assumed that there's limited liability, and liquidation and valuation. Okay, that's a subtle point that needs to be changed. So I would say that they are valued, right, according to this equation, but at the same time can also be used to fulfill obligations. That's the story, right? Whether or not this is a nice story or not is a different question, right?
Alex David has a paper with a co-author,
Mm-hmm.
and one of the features of his paper is that who goes bankrupt is endogenous.
Is endogenous here,
And
yes.
It depends on which claims get paid. And I'm not sure where the other side of these CIJs are. So your counterparty.
So the CIJ is J owns shares in company I. So
Yes,
the way you see it,
is given.
they sell their shares and they
Their
get the
shares
cash
or
and
their-
they pay out.
Yes, yes.
their
Yeah, but
They
in the
liquidate
case
their shares.
in the case of the illiquid assets, the story is a little bit different. There, the idea is that price impact comes only from those shares that must be sold in order to fulfill obligations, and the rest is mark to market. That's just the story here. But anyway, I think we discussed this also now in detail, what this model is and maybe where there are shortcomings of the model, no question about it. You pointed this out very clearly. Let's us just move on so that we also see a few numerical case studies. What do? We have the system here. You can integrate all these other papers into the model we have. In particular, the Cifuentes model, the Amini, Minka, Filipovic model, all that stuff can be implemented in the model. Amini, Filipovic, and Minka and Cifuentes, they have this illiquidity story, which we also adopt here, right? The difference between their paper and our paper is that we also have bankruptcy costs and cross holdings and direct liabilities, but the illiquidity way, how that is computed, is identical to the Amini, Filipovic, Minka, and Cifuentes paper, which doesn't make it better. I agree with that. Just to
I asked them the same questions.
you are completely right to ask these questions, no question about it. And you are also right that this is something one should clearly describe and point out what exactly is assumed. Okay, so what we have is we can prove that there exists a largest and smallest price payment equilibrium. That is proved by Tarski's fixed point theorem. You can also do this in this large system. You can come up with an algorithm. You can also analyze some toy systems and look at the behavior. But now I want to look at the numerical analysis of the defaults. So what we do is we assume that the liabilities inside the systems are generated according to a random mechanism that is encoded by two parameters, C pi and T pi. So that are the relative liabilities, right, of the banks to each other, right? And R and S, that is what the banks have in the liquid asset and the illiquid asset, that will be computed from pi using parameters delta and rho. So that are deterministic parameters. I'll explain how that works. C, that are the cross holdings. That's also this metric. So it's also a network, of course, right? Because it tells you how much do I own of the other guys. So it's a network. This is also randomly generated, right? And I explain how that works. So in the end, we have a model which depends on these parameters here. C pi, d pi, generating the pi randomly. D rho, generating the R and S. Alpha, beta, that were the bankruptcy costs. Gamma, that is this price impact parameter in the inverse demand function. And C and D generating the C. We assume that we have 100 banks, and we assume that the total liabilities, the total liability vector is just consisting of ones, right? Just for simplicity. So every bank has liabilities of 1, right, in total. So how do we compute now this relative liability metric? So we use an Erdős-Renyi random network, which has a so-called level of integration and a level of diversification. So how does it work? You take a bank, and then what you do is you randomly sample links to other banks, right? You have n-1 other banks, right? Yeah. And then you just toss a coin, right, for each of the banks and see whether or not you have a link. So what the probability of having a link? So the probability of having a link is given according to this diversification parameter. The expectation of banks to which you have a link is just the d pi. Right? That's the expected number of links to other banks you have, right? So that's the d pi. C pi is a different number. C pi is the fraction of your liabilities that are inside the banking system, right? And 1 minus C pi is a fraction of your liabilities to the outside of the banking system. So for this reason, the C pi is called the level of integration, how much is in the banking system. And d pi is the level of diversification. How is that spread around, right? So there are these parameters. That's how it works. So that's a simple random mechanisms to generate the links. So then we compute the external asset holdings and the cross-holding metrics. How are the external asset holdings computed? Well, we have two parameters. One is called a capital buffer, and the other one is a parameter rho, which is a proportion in the illiquid asset. And so the point is that we compute the random amount that is necessary in order to keep the banks from defaulting if we don't consider cross-holdings. This is the first number we compute. It's a random number that depends on the pi, right? The randomly sampled pi. And then we have this capital buffer, and we just multiply this h by 1 plus delta to get the total number of external assets the bank has. So this is just a convention to do, right? It's not so important. It's just a way to do it, right? You look that you are solvent enough, right? Right? And then you split that according to a parameter rho. This is more important. So this is really important. The parameter rho is important. The parameter rho is a proportion of the illiquid asset. And R, 1 minus rho E, is the illiquid asset, and S is rho times E is what you have in the liquid asset, illiquid asset. So that's it. Rho is important parameter. How much do I have as a fraction of my total endowment in my illiquid asset? That's the parameter we need for the case studies. And the C is also generated randomly according to this Erdős-Renyi network in exactly the same way as a pi. But it has, of course, new parameters. A level of integration, right? What is the fraction of net worth that is held by the other banks? C, right? What is the fraction of net worth held by the other banks? And D, that's of course just an expectation. It's the expected number of shareholders I have in the banking system. The expected number of shareholders I have in the banking system is a D in the random mechanism, right? So that's how we set up the system. And now the procedure worked as follows. You fix the parameters of the model, you sample P and C randomly, you derive the random quantities R and S from the samples, and then, after you've set up your system, you sample one bank at random and you kill it, right? That's what you do, right? You fix the system, You take one bank and you smash it, right? Z. And now, once you smashed one bank, you compute the equilibrium according to the equilibrium mechanism I explained before, right? And the equilibrium corresponds to a number of defaulting firms, or firms that are insolvent. So for each simulation, you count the number of firms that are insolvent, right? And then you repeat this experiment a large number of times and compute the sample average and the standard deviations of the number of firms that are default, that are dead, right? So the contagion mechanism is you have a randomly generated economy, which can easily be characterized in terms of a few parameters. You smash one bank at random, and then you see what is the contagious impact in the system. That's what's done. And here are the case studies. So this is something I really should do, because otherwise it's maybe not so clear what results can be got in this setting. So here we have a first picture which shows us the number of defaults, the expected number of defaults, as a function of the bankruptcy costs. So we have this parameter alpha, which is the external recovery rate, and the parameter beta, which is the internal recovery rate. And we have here the C chart, and black means there are on average no defaults, and white means there are many defaults. So you see how decreasing the fraction that is recovered, of course, increases the number of defaults. And what you also see is that the regimes with, on average, no defaults and many defaults are very large, and that the transition area in this model is very small. However, I have to mention that the model we look at here, this picture, this is just the model Eisenberg-Noé plus bankruptcy cost, and all the other effects are set to 0. No cross holdings, no illiquidity. So it's really just the setting of Rogers and Ferrat, right? That's the setting we have here.
So if I understand correctly, it means that you have 100 banks, and
Yes.
even with 95% recovery, so 5% bankruptcy cost, you get 90% of the banks that default.
Yes, given the parameters we have. Yeah.
So that doesn't seem very...
Yeah, you know, the parameters we set in the beginning, of course, you can change them around and look at different case studies. This is just due to the parameter choices we have. You're completely right, and we haven't calibrated them to empirical figures, except for the number C pi, which doesn't show up yet here. But you're right. With other parameters, you get different pictures. But still, what is visible is that, of course, the number of defaults on average depends on both parameters alpha and beta, and that the regions in which the average number of defaults is large or small, that they are large and the transition area is small, right? This is also what you see here if you look at fire sales. So here you have the parameter gamma and the parameter rho, and gamma gives you the parameter that tells you how illiquid the market is. The price impact parameter is this, and rho is a parameter that gives you the fraction of the illiquid asset holdings you have. And if you increase illiquid asset holdings, of course, it means that default is much more likely. The same is, of course, true if you increase here the price impacts, then, of course, default becomes also more likely. And what you see here in a model which has only the Eisenberg-Noé network plus the fire sales, no bankruptcy cost, no cross holdings, this model, right? Then you see that there's a rather sharp boundary, and this boundary here also follows a power law in this case, and the transition area is very small. And we will also, in a couple of minutes, I'll try to finish rather soon, but in a couple of minutes we will also look at joint effects, where I look at these figures here with the introduction of cross holdings at the same time. And we will see what that changes, right? So this is just separate effects, right? So here's a power law. I mentioned this. Let's forget about it. So this is another model. So this is a model here where we consider the Eisenberg-Noé framework jointly with cross-holdings. But we don't look at bankruptcy costs, we don't look at fire sales. So this is only cross-holdings, right? And so cross-holdings, there's a level of integration, so that's the fraction of liabilities inside the banking system. And we have the diversification, which is basically the average number of shareholders each bank has. And one sees, if one looks at the level of integration of the cross-holdings, that the number of defaults can, in this model and this particular case study, be really decreased to, on average, to 0 for when you increase the level of integration, right? This is observation from the numerical case study. However, if you look at the diversification, which is the number of shareholders a bank has on average, you see that up to some level, around 10 shareholders in this economy of 100 banks, this has some impact on the average number of defaults, but then it's almost constant, right? So that's the observation. So it seems that the level of integration of the banking system can significantly, in the model, reduce the average number of defaults, while the level of diversification has only a very limited effect, up to 10 banks in a system of 100 banks.
So, I'm sorry, I missed the very first part. These are equity cross-holdings?
That are the cross-holdings I introduced, yes.
So this is like the Japanese banks at one point. They
Mhm.
wanted to look really big, so 90% of what I own is shares in you, and 90% of what you
Yes.
own
Yes.
is shares in me.
Yes,
And only 10% is actual
yeah,
assets, so you look really huge.
yes.
But I guess you have to be very careful about how I guess it's subtle on how those other parameters are picked. You don't want to
Yeah.
exogenously pick the fraction of liquid and illiquid assets when.
Yeah, I see your point.
The question is, what other assumptions, other things equal should be what in this model?
Yeah,
Can you talk a little bit about what is staying fixed? Is it?
Yeah. Everything else is staying fixed, and just the C parameters
Well,
vary.
everything else, we know from thermodynamics that it depends what you mean by everything else.
Yeah, all the other parameters. So we have here the list of parameters: the n, the p, the c pi, d pi, delta, rho, alpha, beta, gamma, c, d.
The question I think is when you increase
Yeah.
your cross holdings,
Mhm.
does it mean you're increasing your asset size, or are you keeping the same asset size and then allocating differently?
Yeah, no, all the parameters stay the same, and we then generate the system again according to this mechanism. The only thing is that in the whole procedure where the samples are generated, the C pi parameter is changed. So the C pi parameter is just the fraction of liabilities that stays inside the banking system. So
And how do you choose the sizes of the liabilities? They're all equal?
the sizes of the liabilities are, yeah, you are right. They are chosen in the following way. You pick a bank, you sample the links to the other guys, and then you distribute C pi across those guys that have been sampled. So the total, equally, so the total number of liabilities inside the banking system for each of the bank is fixed. The only thing that is random is how you spread it across
And
the other
in the
guys.
example you showed, integration, what's the interdisciplinary parameter?
Yes, the integration is a C pi parameter that is
Yeah,
here.
in the example you showed right now.
Ah, okay, and you mean these examples? Sure.
What's the
The C pi, okay, the C pi parameter. Yeah. Let's see.
It's small.
Yes.
It's small.
The CPI parameter,
Okay,
that's,
don't worry.
yeah,
No, but
I don't have it here.
So I think
It's
the
in the
graph is
paper.
easy to understand. The second graph.
Yeah.
This graph, the second graph. So it stops at 10, the diversification.
Yes.
That's square root of 100. That's
Yes.
because
Yeah.
you have, with small probability, you will have one link, okay? And then the neighbors are linked to their neighbors. So you have cross-holding, I has cross-holdings in J,
Yes,
and J has cross-holdings in K.
yes,
And if you look at your fixed point equation,
yeah,
you're valuing the cross-holding of J in K as a fraction of your cross-holding.
Yes,
size.
yes.
All this is taken into account by your
yes,
equation.
yes.
So, but for this, there has to be a link in your graph, in your integration graph.
Yes,
So if you have an Erdos-Renyi graph, okay, you will have probability P to have a cross-holding, and then probability P squared to have a second order cross-holding in some of the
yes, yes,
And then
completely right.
After that, it's really
It's
very
done,
small.
kind of. Right, yeah,
So
I see your point,
You
yeah.
will, if I have, I will have
Yeah,
at
yeah.
most
Yeah.
10, no, I will have at most 100
Yes,
the second order cross-holdings.
Yes.
So square roots is 10.
so I'm basically done.
And if I go
Right.
beyond 10, I'm just recycling cross-holding is the same.
Yes, yes.
I cannot really gain.
Yeah, I see the point. This is also, I think, a good observation. It turns out that the effect here is not as strong if we introduce the other effects, but we'll see that, but it still stays around. And so, yeah, your explanation is probably exactly pointing out to the right thing. And if we introduce other effects, they are just other effects of lower order that shifts us a little bit around. We'll see this in a second. Okay, so-
when we have this increased integration,
Mhm.
is this, I want to ask my
Yes,
other question.
sure,
again in a
sure.
little different way. If we look at what the banking system is holding,
Yeah.
the total holdings of things outside the banking system and
Yes.
so forth, is that changing when you go down that curve? Is it a big-
Yes,
is
yes.
it-
So
so
C is a
it-
fraction. So C is a fraction. So C is a proportion
So in
of the
effect-
liabilities inside the banking system, and 1 minus C is a fraction of liabilities outside
So
the
it's-
banking system.
so
So it's
it's
really a
a
fraction
fraction-
that
It's
changed.
a fraction, and the
Fraction.
total amount is staying the same.
Exactly. The
So-
total amount is always
So-
fixed at 1.
So this is a smaller banking system. So when you go down that curve and you increase this level of integration,
Yeah.
one of the things that is the banking system is doing less work, it's doing less things on the outside.
That's right. That's right. That's
So,
right. Yeah.
I think this may confound, a smaller banking system has less to fail with the,
Yeah.
with the benefits of the cross-holdings.
That-
I'd like to see an exercise
Yeah.
where you look at the net relationship of the banking sector with this.
To the
rest of
outside
world.
stays the same, right?
Stays the
Yeah.
same,
And
so
then
it's
we
the same
vary this
size of the
parameter.
banking system.
I see your
And
point.
then,
Yeah,
that's what I
yeah,
mean
yeah.
about what,
Yeah, yeah.
you know,
yeah,
what are
yeah.
you leaving fixed? Maybe you
Yeah,
should,
yeah.
if,
Yeah, yeah.
if part of your assets is
Yeah.
holdings of other banks,
Yes.
so you look 10 times as big as you really
Mhm.
are, maybe you should increase total assets by a factor of 10 too.
Yes, yes.
But here,
I
there's
see
no
the
bankruptcy
point, yeah.
cost here
Mhm.
in this.
Hmm?
No bankruptcy cost in this.
Yes, but we have slides with bankruptcy costs and with everything together. So just one thing I also want to mention is we also looked at standard deviations. So if you look at this picture here, for example, right, this is just the average number of defaults here simulated. And of course, this average number of defaults has also a distribution, right? The average number of defaults, because we have a random mechanisms to set up the system. And so the random mechanism also makes sense because in terms of very few parameters, we can set up the system without specifying basically every links in a deterministic manner. So having a random system gives us a better way to really capture structure with a few parameters instead of having a deterministic thing where basically we have to make sure that every link is specified, right? That's the reason why we want to use a random system to set it up. But still, in the random system, of course, the way how the links unfold and how we pick this bank that we kill will influence the number of defaults in the end. And so we also look at standard deviations, and this is what comes out of it. So you see here small standard deviations is black and high standard deviations is white. And what you see is that in these transition regimes, with an intermediate average number of defaults, you have actually a high standard deviation, while if the average number of defaults is very low, the standard deviation is actually very small. And so what does it tell you? It tells you that if people just look at the average number of defaults in their analysis, and most of the literature has done this, I think we are the first to consider the standard deviation in these model exercises. Not completely correct. I'm looking at these equilibrium papers, right? I quoted, right? There are other papers doing other things that, of course, do such an analysis, right? Just to get that right across. But the point is that in these regimes with an average number of defaults, you have this high standard deviation. So it means that here you basically have a high systemic risk as well, because it's very uncertain what the outcome is in the end, right? The average number itself doesn't tell you too much. There's a high variance around it. You see actually the same thing also if you look here at this other picture with the integration. That is this picture here, right? So here in the middle part, there's also high standard deviation around this.
I don't know why standard deviation is the right thing, because in the region down there, everybody defaults. So I would say it's high systemic risk.
Absolutely, yeah,
Standard
yeah.
deviation is
No, no, no. We are just pointing out two different things. Point one is, no, I agree with you. No question about it. There are two levels of systemic risk you have to consider. And systemic risk, of course, is related to the distribution of the adverse event or the adverse parameter or random variable you're interested in. So you're completely right. If we have a large number of defaults, right, that's bad. It's high systemic risk, of course, no question about it. But what I'm just saying is that looking at the average alone is not sufficient. You also have to consider the distribution. So if you just consider the average, you might claim that being here, right, here at this level, this is a really low number of defaults. This is not large systemic risk. And I'm just saying that just looking at the average number of default is not enough, because if you do that, you neglect that, let's say here at this point, you have a standard deviation around this average, which is of this size, which means that randomly you can also be somewhere else, right? This is just what I pointed out.
Low regime, but when the average is 100 and it's a random variable bounded by 100, then it means everybody defaults. So there's no doubt that down there.
No, you're completely right. So what I'm just saying is that if you look at the average regimes, you also have to look at this kind of second order effect. What does the variance do around the average in order to gauge the systemic risk? This is just the message, right? Yeah, but you're completely right. If you are in the extremes, then the standard deviation is not so relevant. If you're here, you have many defaults, okay, then having a large standard deviation, that just means that around this high number of defaults, you have some fluctuations. Systemic risk is high anyway. While here,
systemic risk high or low is a red herring here. I think I would say that when you're in that intermediate regime, whether they're defaults doesn't just depend on the parameters, depends on the network structure.
Yes,
which is drawn randomly.
Exactly.
So the network structure is a relevant factor in whether it defaults.
Exactly.
If you had a standard deviation is very small, then I would say these cost parameters are driving whether or not there was default.
Yes.
It doesn't matter much about the network structure.
Yes. Okay. Yeah, that's a good point.
And rather than get into this question of what you mean by systemic risk is bigger or smaller. I think that would be a more pointed way of expressing.
That's a very good point. That's a very good point. Because it's basically where the sampled firm is inside the randomly generated network. So the actual random network structure and the position of the firm, that's what drives.
So the random generation of the network matters a lot. So which means that whether or not there's default depends a lot on the network structure.
Yes, exactly.
Yeah, but if you don't have crossover links and
they come,
cells, then this is a special case of the models we analyze with Amini and Minka, and there you have a lot of large numbers. You can show actually that the number of defaults
Mm.
has a limit in probability as the network size increases.
Mm.
And so actually, asymptotically, it doesn't depend on the sample you simulated, but only on the distribution.
Mm.
So then it justifies the fact that you can actually extrapolate your observations to some general feature of the
Mhm.
model, rather than saying, well, maybe if I generated a different Monte Carlo sample, it would have been different. Because people can say, yeah, our sample dependent.
Yeah, well, the qualitative features of the graphs I show, they are always the same in all the simulations we did. We did many more than I present here, right?
Yeah, but I think there's a reason. There's an underlying law.
Yeah, okay.
For the number of defaults, for other things. I don't
Yeah.
know.
So let me just come here now to the Eisenberg-Noé model with bankruptcy cost and fire sales, right? So this is now both bankruptcy cost and fire sales, no cross-holding. And this is now corresponding to this graph here. So we have here this power law, which really clearly separates a number of defaults which is very low and a number of defaults which is extremely high. So there's a clear separation, almost no transition area. And if we introduce in addition our bankruptcy cost, you see that this transition area becomes more spread out. This is the effect, basically what you see, right? So here we also have joint effects now, an Eisenberg-Noé model with bankruptcy costs, cross-holdings and fire sales. And we do the analysis here now on the level of cross-holdings. So what you see if you do that now on the level of cross-holdings is that if you increase integration, you can again decrease the average number of defaults to 0, but in comparison to this graph, this is basically moved up, and the effect occurs only if you have very large levels of integration. And here, this is what Rama also mentions, this basically square root structure. If you have this diversification, then of course, if you have 10, which is square root of 100, you're kind of indirectly linked anyway, with high probability to everybody else, at least second order, not first order. But what one sees, if one introduces also these other effects here, then one sees that this effect remains, but that some higher order effects also occur. And these effects can then be seen by this curve having some slope which is going down, right? So there is some effect here in this range to this kind of second order connection in the cross holdings if you introduce the other things.
So EN means what?
This is just our notation. EN means Eisenberg-Noé,
Oh,
and B bankruptcy costs, C cross holdings, and F fire sales. Say for Eisenberg-Noé we use 2 letters, and for all the other things just 1, right? Because somehow we have the feeling Eisenberg-Noé that's easier to remember if we have an EN, right? Probably we should have written E and a little n or something like this, that one knows it's one word, right? But that's what it is. Eisenberg-Noé, bankruptcy costs, cross holdings, and fire sales, right?
So in your case,
Mm-hmm.
if I read well, diversification is always good. It always decreases the number of defaults. More connectivity
Yes.
in the system always tends to decrease the number of defaults.
Yes, that's how it works. It's not so significant, right? So you are kind of bound somehow in this model.
no, because
But this
is
helps, but
diversification in the
is the average number of shareholders. you have.
shareholders.
Yes.
Okay.
Yes. And
Shareholders.
the C, that's the other
There
thing.
are 2 networks.
But
Yeah.
your comment, right, pointed out that maybe the C analysis we do is maybe not somehow the most appropriate one, right? Because we don't leave
I guess,
this outside fixed, right? We just shift it around, right? And what you said, it might be better to leave the total size of the liabilities to the outside constant, and then given that, then change the size of the liabilities inside the system,
yeah,
right?
yeah.
Yeah,
No matter,
yeah.
no matter whether we take the derivative
Yeah.
of temperature with respect to pressure at constant volume,
Yeah.
or constant something else.
Absolutely, absolutely. Yeah, I got the point.
Okay, so
So,
can you, so in
Uh-huh.
this model,
Yeah.
this thing to this question, if you, there are 2 networks really. There's
yes, yes,
banks can lend to each other,
Yes.
and banks can own shares in each other.
exactly. Yeah.
So if you fix the size, I'm not sure if the size is fixed in these comparisons, but if you fix the size,
Which size?
the size of the bank portfolios, and you change the capital structure in it, so you have different
I see.
proportions of shareholder,
Yeah,
debt
yeah,
holder.
yeah.
So, is that what you're doing here, or are you changing the size when you change this parameter?
Yeah. So what we do here is we fix the size of total liabilities each bank has, and we fix the number of banks, and then this was your point, right? Then we change the fraction of what liabilities are inside the system and what liabilities are outside the system, so that this parameter. We also change, of course, the way how the liabilities inside the banking system are spread around among the companies.
When you change this, are
Yeah.
you changing the leverage of the banks, or are you have a fixed proportion of debt and equity when you change the parameters?
Yeah, so that's this here. What we do is, once the pie is given, which is a liability structure, we then compute, if we neglect the cross holdings, what is the amount of value of assets that the banks need in order to fulfill the obligation. And that's computed as a random number h. It's random because it depends on the random pi. And then we have this amount that the bank needs in order to be solvent, and we multiply that with 1 plus delta, and we have a capital buffer. And now, after we've done this, right, we have this proportion parameter rho, which tells us how to allocate that between the liquid and the illiquid asset. That's the mechanism, right? So we always have, for each bank, exactly the amount of capital it needs to fulfill its obligations times 1 plus delta, right? If the assets were completely liquid, right? If the assets were completely liquid. They are not, right? They are not. But after we did that, so the banks would be all in good shape. If everything is completely liquid, then we split this into the two parts pairing to the parameter rho. That's how it works, right? So we basically have the system, neglecting cross-holding, a little above solvency given the sampled pi. That's how we do it. If all the assets were liquid, right? And then we do the split with the liquid and illiquid asset, and of course that can change the picture, right? Because now the price impact comes into play, but it's controlled exactly by the rho, right? So it's very clearly specified how we split it, right? And that can already trigger insolvency, right? If the rho is large, that can already kick the system out if the delta is small. So maybe at the end, just let me mention that we also did this analysis of the standard deviation also in the joint model, and the same comes out of it. So I think you phrased this very nicely. We have a random network, we have a random position of a bank, we compute the average number of defaults, but the actual number of defaults depends on the sampled network and the sampled position of the bank. In the case in which we have an intermediate average number of defaults, while in the extremes, right, the networks don't matter that much, because then the situation is either so good or so bad that a little fluctuation of the network doesn't cause too much change. But in the intermediate regimes, it again does. Okay, so yeah, I don't have to go through the conclusion. I went over time anyway, but I think it's pretty clear what we did. What we basically did is we came up with this fully integrated model that's currently missing in the literature based on the Eisenberg-Noé model. So all these models that do exactly Eisenberg-Noé and one thing more, right? And so now we have a model that does Eisenberg-Noé and all the other things together. So there you can also prove the existence of equilibria, come up with an algorithm, and do some numerical case studies, and we did that based on Erdős-Renyi graphs, as mentioned, right? Okay, great, thank you very much. Yes.
When the number of defaults is very small, like 1,
Yeah.
is there another equilibrium at which there's many defaults that just isn't reached?
So,
Or is that equilibrium unique?
no, the equilibrium is not unique. In this case, it really depends on the parameters of the model, but you have a largest and a smallest equilibrium. So how you have an equilibrium with the largest number of defaults and one with the smallest number of defaults, and you have some equilibria in the middle. And in the numerical case studies, we looked at the largest equilibrium with the largest number of defaults. That's what we did, right? But you don't have uniqueness in this case. And you can also illustrate that there are examples in which you really do not have uniqueness. I have here an example. But this is the result, right? You have a largest and you have a smallest equilibrium vector, or these are equilibrium vectors, and all the other equilibrium vectors lie in the middle. But this is not necessarily a connected set, right? So you have not the possibility to draw a line between the one thing and the other one and say, well, in the middle I always reach some equilibrium. This is not the case. I also have a counterexample here on my slides, which I skipped due to time. And you can also construct very simple examples, right, where you do not have uniqueness of the largest and smallest equilibrium. So this example with 2 firms would already be an example. And also this is an example where the greatest and the smallest equilibrium are not connected through a line, right, in Rn plus 1, right? You have Rn plus 1, you have n firms, so P is n-dimensional, Q is the other parameter, so you have Rn plus 1. You cannot draw a line between this and this such that all points on the line are equilibrium. It's not possible. I also have here counterexamples which show that that's not possible. So the situation is more involved. And for that reason, if you do numerical case studies and you don't have uniqueness, you have to say on what you focus on. And we focus always on the biggest one, right? Could do the same with the smallest one, right? Or you could also require that you only look at system where you have uniqueness, but then you have to impose, of course, extra conditions, right? Yeah. So Tarski's fixed point theorem does not give you uniqueness. But, of course, if a theorem doesn't give you uniqueness, it doesn't mean that you don't have uniqueness. It could be the case that you just didn't find it, right? But here, in fact, there is not uniqueness, right? Which is shown by the examples.
Yeah, it is already true in Eisenberg, no?
Yes, yeah, you're completely right. In Eisenberg Noé, they also don't have uniqueness, which really relies in their model just on the fact that there can be somehow payments which go either way somehow, right? Or on the ring or something like this, right? Yeah. Okay, great. Thank you very much. Thanks.